introduce our speaker. Jason is the creator of the Concurnas Programming Language and the founder of Concurnas Limited. He wrote his first computer program, aged 9, and has been coding ever since for over 25 years. Jason has written and led teams developing algorithmic trading systems for some of the world's most prestigious investment banks, including Bank of America, Merrill Lynch, Deutsche Bank, and JP Morgan. Passionate about technology and programming, and making Concurnas the best programming language it can be. We're not building Concurnas or consulting in Jason today. And without further ado, over to Jason.
So, as Paul introduced me just then, my name is Jason. I'm the creator and founder of Concurnas. I've been programming since age 9. Actually, the first computer program I ever wrote, I wrote on an old Apple IIc, which I found in the attic of my parents' house at the time. I was lucky. I found a floppy disk, an old 5-inch floppy disk holding a copy of Apple Basic, and I found a tutorial and an instruction manual. And ever since then, I have been pretty much coding, non-stop for about 25 years. And most recently, I've been building algorithmic trading systems in JP Morgan, Deutsche Bank, and Merrill Lynch before that. And those systems were for high-frequency trading, algorithmic trading in the foreign exchange space. And we were doing two forms of concurrent programming. We were doing what I like to refer to as explicit concurrency and implicit concurrency. So the implicit concurrent programming that we were doing would be a case of, so here's the hardware resources that we have access to. Maybe we have a single machine, like a quad-core machine, or an octo-core machine, or maybe we have access to a grid of computers, maybe we have access to a cloud. Perhaps we have some slightly esoteric but more commonplace nowadays hardware sort of in the form of a GPU. How can we make best use of that compute capacity in order to, say, do derivatives pricing or trading model simulations, etc.? The other sort of side to that coin was what I like to refer to as implicit concurrency. So when we were building trading systems, we often had multiple feeds of market data or signals that we would derive from those market data. And then the problem itself is intrinsically concurrent. You had to be able to process all of that information pretty much at the same time or prioritize it in one way or another. But then you'd be making decisions based off of that of that data on a real-time and immediate basis. So performance was very, very important, and being able to leverage the hardware that we had access to in order to solve those implicit and implicit concurrent problems. So this sort of engineering was quite challenging, even for really very talented world-class engineers. This was a real struggle, and it would take up a lot of engineering time. So in 2017, I left to create Concurnas, which is a new programming language which is designed specifically for solving these sorts of engineering problems. So without further ado, Concurnas. So it's a new programming language. It runs on the JVM, so the Java Virtual Machine. This surprises some people, but we'll get into the reasons why that decision was made a little bit later on. It's easy to learn, so it has it's a Pythonic syntax. So you don't necessarily have to be an expert in computer programming to be able to be productive within it. It's also high performance, so we've managed to not sacrifice performance in order to get that ease of use. So we have effectively the best of both worlds. I've heard people describe it as being a sort of marriage between Python and Java, with a sort of a dash of languages such as Erlang, which have a very similar sort of concurrency model that is exposed within the language. And it's an easy to scale language. So the idea is that one can take the same code that one has written on one's single core or what's more likely a quad core machine, and be able to, with very, very little modification, be able to run that same code on, say, sort of a server type machine which has many, many more cores, maybe 64, maybe 128, and then the next step would be able to take that same code, maybe with some slight modifications, but be able to run that on a grid environment or in the cloud. So you're not having to go and reinvent, to do all of your work all over again every time you need to scale up. So your code scales in support of the business that you're supporting through that code. It's also designed to be a multi-paradigm and also multi-domain language. So the areas that we're really targeting with the language are enterprise computing, scientific computing, numerical computing, and also finance. The language is a general purpose language, but I feel that these sort of areas would benefit most from the contributions that Concurnas provides. If you were to ask me what areas probably wouldn't benefit, it would be things like, say, video games. So if you're building a video game engine and you're doing a lot of low-level engineering in C, C++, probably wouldn't benefit from this. That being said, there are video games such as Minecraft which were implemented in Java and on the Java virtual machine, which is the same virtual machine that Concurnas uses. So actually, yeah, maybe you could write a video game in it. It's up to you. And best of all, it's open source. So it's licensed under the MIT license, which is the freest and most permissive open source license available. So you can essentially download the code and do more or less whatever you will within that code. You can put it inside your commercial software. You can redistribute in accordance with the terms of the license. It's very free. It's very open, and so let's now look at the obligatory hello world. So here's a first sort of snippet of Concurnas, and don't worry if you don't get all of this right now. We'll go through in a lot more detail about all of the specific interesting points that are raised in here and others later on in the talk. But first of all, we can look at this snippet of code, and we see that there's actually quite a few things going on here. So first of all, when we define functions, they may exist in isolation. So in traditional object-oriented languages, such as Java, it's probably the most well-known, you're obliged to define what you would call a static method. So a function like this one, in order to calculate the greatest common divisor, you would be obliged to define that within the context of a class. Whereas in Concurnas, you're allowed to define that just on its own. So it's very similar to the way in which you could do so with Python. The function return type in this definition is implicit. So Concurnas is what's known as a type-inferred language. And you see this with the creation of the variable y here. So although Concurnas is what's known as a statically typed or strongly typed language, in that it offers it offers type safety, it presents the syntax, or the facade rather, of a dynamically typed language. So in that way we get the benefits of the strongly typed type system that you see in languages such as Java, with also the benefits that you see in languages such as Python, which is a dynamically typed. And Concurnas is able to achieve this by using a method known as type inference, which was a technique that's popularized within more functional programming languages, like Haskell is the sort of the classic example there. And so in this case, our function here, which calculates the greatest common divisor of an integer, so x and the number 3, Concurnas is able to infer that the return type of this function is an integer itself, and it's also able to infer that the type of y is also an integer, just based upon the fact that a value of 3 is initially being assigned to it. Concurnas contains the usual set of imperative programming constructs insofar as program control is concerned. One of the special features within Concurrens is that all types can be used in place of in cases where a Boolean value is expected. So in this case, the code will evaluate and ensure that y is not equal to 0. If it's equal to 0, then that's equal to false, and then it would escape from this piece of code. Otherwise, it would continue with the iteration. Concurrens also supports tuples. So here we have an example of tuple creation and also the tuple dereferencing. And it is your choice as to whether you choose to explicitly use the return keyword. So if you admit to the return keyword, then the last expression in a function will be considered to be what is returned from that function. We also have a feature here. So this is an interesting story. So we have a range expression, and when one is creating a programming language, one does one's research and you speak amongst your friends and your peers and your colleagues and your potential customers and say, well, what are the things that concern you, and what things do you want to see in the language? And this feature, so numerical range expressions, I wasn't too keen on. I thought, well, whatever, it doesn't sound very important, but people were very, very, very keen on this. And when I first presented this to some large potential customers, they were very, very excited about this range operator for some reason. So I'm glad I included it against my own personal judgment. So what this piece of code does is that it'll iterate between and including the numbers 101 to 105. The next and the most interesting thing is this line here, which you see is terminated via use of the bang operator. And the bang operator says, take whatever code was referenced either in the previous block or the previous statement. So in this case, we're doing a method invocation to print out to our standard output. Take that piece of code and run it concurrently. Run it within what we'd call an isolate, which is essentially, it's a lightweight thread. And we're going to delve into more about this concept a bit later on in the presentation. But for now, it's enough to just to recognise that this is an instance of concurrency. So this line of code will run concurrently. So we're able to run these instances within our for loop on a concurrent basis. We also have string formatting, so making use of the brackets in order to embed. You can actually embed expressions within a string, which has received some positive feedback. And notice here this expression, so system.out.println. That sounds a lot like Java. Well, yes, it is Java. So when one builds a programming languages are more than just syntax and semantics. Maybe like 50 years ago, somebody would deliver a programming language specification and they would deliver a compiler, and then that would be it. They'd brush their hands and job done. But nowadays, of course, when we think of programming languages, we think of things like the documentation for them, we think of the standard library, we think of the other libraries that other people have built for them. We think of all of our build tools, we think of all of our developer tools, our IDEs, etc. And one very, very important thing that a programming language really needs to have in order to be successful nowadays, at a bare minimum, is some form of standard library. So Concurrens, by virtue of the fact that it runs upon the JVM, gains access to the Java standard library, of which system.out.println is a member. So also, if you have existing code which is built in Java or a JVM language such as Scala or Kotlin, you can use that code within Concurrens as well. So we run this code, and what output do we get? Something like this. Your output may vary. Why? Because we are actually running this execution here on a concurrent basis. So if I was to rerun this piece of code again, or if you were to rerun it, we would expect to see a different order of which these isolates would complete their execution. So what problems was Concurnas designed to solve? What's the motivation behind all of this? So these days, as developers and as coders, as engineers, as data scientists, and of users of computers, we are expected to deliver solutions to problems. And I don't think we've ever had to work so hard and so fast. And the expectations have never been higher upon the individual and the corporation and the team. Part of it is because we have amazing tools nowadays. Like we have amazing languages like Java and Python and C and C++, and we also have amazing hardware, particularly in the form of GPUs, which are massively powerful. It's like having a supercomputer inside your machine, and we'll get into a little bit more detail about that and the support which Concurnas has for it a little bit later. We also have amazing libraries and frameworks, say for doing machine learning. That's been a big amount of growth recently, and but developer performance is something that it needs to be consistent, and actually has been expected to improve over the years as these tools have been available. So we need our languages to be those which enable developers to be productive, whilst at the same time not sacrificing that performance. These days, teams that we are within are very heterogeneous. So, not everybody is a software engineer. I think it's actually quite unusual for there to be teams that are full of just software engineers. Usually you have domain experts, usually you have data scientists, usually you have machine learning experts, all embedded within the same group. And so to expect all of those people to be able to speak the same common language in the form of code, I think is quite reasonable. But if the bar for understanding that code is very, very high, then all that you're going to do is you're going to potentially exclude people, or you're going to make it more difficult than it needs to be in order to get work done as a team. At the same time, it can be very useful at some points to be able to still have the option to go low level, to go very, very detailed, but present a facade that's much higher level that your team members can use. But one of the big motivators and one of the big factors for Concurnas is that CPUs nowadays are not really getting quicker. Like if you look between and this is the most up-to-date chart I could find. It only goes up to 2008. Sorry, but I'm pretty sure that after that point, the curve pretty much stays as it was from 2015 onwards. If we look at from the sort of early 90s. Mid 80s to sort of the early noughties, your CPU pretty much doubling clock speed every single year. It's pretty impressive. These days, maybe 3% quicker. And whilst the CPUs themselves aren't getting intrinsically quicker, they're getting wider. So it's possible now to buy, I think you can get like a 64 core machine, 64 core CPU for, I think it's about $6,000 or $4,000, something like that. It's affordable to have this massively parallel CPU within your machine, but the actual cores within that CPU, they're not really running that much quicker. So this really obliges and forces the developer to think, okay, well, if I'm going to be making use of this compute power, I really need to start thinking about designing systems to operate in a concurrent manner, either explicitly or implicitly. And the same story is told with GPUs as well, which we'll cover in a little bit more detail later on. So people say, well, look, why create a new language? Can't we just use what we've got already? And the answer is yeah, to an extent. So first of all, the first motivation for creating the language is that concurrent programming is really, really difficult. So even with world-class, really talented engineers, I think it comes down to the thread and lock model of concurrency with shared mutable state is just very, very difficult for people to reason about. And so when I was doing research into solving this problem, I was researching alternative methods to the thread and lock with shared mutable state model, and I think I've touched upon something which we'll explore very soon. So principally, Concurrens aims to solve that concurrent programming problem. And then people say, well, why can't you just use a library? Yeah, you can. You can use a library-based approach to solve these things. You can take your existing programming language. You can take C. You can take C++. You could take Java, and yeah, you can write libraries to solve the problems. But still, you're working. It's more of a workaround of the actual core problem of the way in which that concurrent interaction is presented to the programmer. You say, okay, well, how about augmenting an existing language? So there, again, this is a very popular technique that's used. Again, it's fine, but you're very much constrained, very much bounded by the restrictions of that underlying language that you're extending. We'll see people. So then people say, okay, well, I know, I've got it. Modify an existing language. Okay, sounds awesome. And the answer I would give to that is, well, good luck, because to put things into perspective. So one of the core components of Concurrens is known as continuations, and the good news is that these continuations are the concept is coming to Java, the Java programming language, and it's coming via the form of a project called Project Loom, and it's taken about 2 years to get to the point where they're looking at actually putting it into the language. So 2 years to develop a core feature in an existing language versus, it's been now 3 years to build Concurrens, but 3 years to build an entirely new language. And I think it's like this for very valid reasons, specifically with Java. At the end of the day, that's a language which has been around for, what is it now, 20 years? Yeah, something like that. And the expectation is it's going to continue to be around for that period of time, ×2 at least. So making very, very big changes and potentially upsetting that ecosystem doesn't really make sense. So there's very good reasons why it's not such a great idea to modify an existing language. Finally, another excellent reason to build a new language from scratch is it allows one to embrace modern techniques and tools such as null safety, vectorization, and present well, as you'll see, an improved, easier to use object-oriented model of programming. So let's now look at the goals of Concurrens. Concurrency. So we've covered this one already. We also want to provide an easy-to-learn, productive syntax. That's optionally lightweight, because actually, sometimes you look at code and what we wanted to do with Concurrens was avoid a situation in which it would become one of these what's known as a write-only language. So it's nice and easy to program in, so people write the code, and then you come back to it maybe a couple of months later, and you're like, what have I written? That's a write-only language. If you're having to rely upon lots and lots of comments and lots of documentation in order to explain the structure of the code, perhaps there's either a problem with the code, perhaps there's a problem with the language. So with Concurrens, we try to aim for the best of both worlds in allowing people to be concise where they need to be, and allowing them to be very, very verbose if they need to be verbose as well. And we also want to present an interface which is doesn't surprise anyone. So one of the languages which we were looking at when I was doing the research into building Concurrens was Erlang, which presents a very similar concurrency model as Concurrens. But the problem and the surprise for people is that it's a functional programming language, and that does put a lot of people off. So with Concurrens, we've taken the approach of being a multi-paradigm language. So we're predominantly imperative, and we also support object orientation, and we've taken aspects of functional programming and incorporated them into Concurrens. And we've also, as we shall soon see, been able to embrace what's known as a new paradigm known as reactive computing. We want to be able to work with large data sets. We want to be able to embrace modern software engineering practices, as we shall soon see. We want the language to be itself extendable, so you can embed other languages within it. And we also want to be able to support domain-specific languages, and that's very important when one is working in a heterogeneous team environment. And we want the language to be around for at least the next 30 years. So it's very important at this stage that the design decisions that are made are going to be ones that we're happy with looking forwards into the next 30 years. And I think, on the whole, we've managed to achieve that. So it's enough of me talking. So let's start looking at some code. We're not going to cover every single aspect of the language because it's an easy to learn language, but it has a lot of functionality. But we're going to cover the sort of core aspects, starting with expressions and variables. So one of the pieces of feedback that I get quite consistently about the language is people say, well, this just makes sense. It looks a lot like Python. It's sort of straightforward to read and understand. How come I've not heard of this? How come I've not heard of this before? And another piece of feedback I got on a Reddit comment was this is exactly how I would design a language if I was to start from scratch. So thank you very much for that. I do appreciate those comments. And I think much of that has come from just the design of getting expressions and variables and variable assignment. The basics, getting that nice and concise. So Concurrent is a Unicode language, so you can define variables, and also here we have a string which is defined in Unicode. We have the usual set of numerical and constants, and we have a Boolean here, and also a character. You can create arrays and matrices in using syntax that is very similar from array-based programming languages like MATLAB. And we've also borrowed the syntax from Python for creating lists. And notice here how the two are very, very similar, and that's by design. We want to just minimize the amount of work that one has to do in order to create a standardized basic data structure such as this. Here's a standard expression, straightforward, a Boolean expression, and an if expression, so all in one line. Again, very straightforward, pedestrian stuff. Variable assignment. So here we have a straightforward assignment with type inference. So an int would be inferred to be of type integer. If we so wish, we can also be explicit about that type declaration. And we also have the option to use var and val. Now, this is a new feature to languages such as Java recently. I think it was added a couple of years ago. This essentially just says, hey, look, I'm creating a new variable. I'm not overwriting one that may already exist with the same name, and in the case of val, I don't wish to reassign it thereafter. So it's a matter of style as to whether or not one chooses to use these. I personally don't in the code that I wrote, but lots of people do, so the functionality is there within Concurrent. We also support the standard set of control flow mechanics. So you've got your for loop, your C language style for loop, and you've got your more modern, so your iterator style for loop, such as here. We support the while loop. We actually just support loop because it actually turns out in general enterprise level programming, while true, so just loop forever, is actually a very, very common construct that appears in many programs. So we thought we'll just add a keyword called loop for it. And then, of course, you can break out of that if you so please, using the standard constructs to do that. We have a while loop here, and you notice what's different about this is that we have attached an else component to the while loop. And people say, oh, well, that's a bug, isn't it? Well, not really, because what happens here is that if we never enter into this while loop, then in that situation we would trigger the else situation. So that actually is quite a useful construct in that it can cut down a lot of code where you have to first check if a certain condition is met, and then maybe you don't want to call this method twice. You need to assign to a temporary variable, and then we do our while loop, and then we have our else block attached below. This just handles this all for you, so it's a much more concise way. You'll notice throughout Concurrens that there are little bits and pieces of syntax and code that are designed in order to make life, that tiny little bit easier for the developer. And here's a standard if else, elif statements. So very, very standard stuff that you'd see in most programming languages. What's slightly different about Concurrens is that all blocks are capable of returning values. So in this instance, and this can be used in two ways. One is just to make code a little bit cleaner. So here we have speed equals distance over time. So distance and time, and then we divide one over the other, and then we assign the result of that calculation to a speed variable, which is returned from the processing that occurs within this block. So if, for example, we were using the distance variable somewhere else in the code above or below this block, this wouldn't then conflict with that definition, so it makes it slightly easier to read. We can also return values from if-else statements. So in this case, a string is going to be assigned to either value 1 or value 2, conditional upon this. And also for loops are able to return lists of values in accordance to what's been the result of the calculation within this for loop. So here we're just doing powers of 2. As far as functions are concerned, so this is an example of the optional verbosity that exists within Concurrens. So all of these 4 functions do exactly the same thing, but you notice here we start with a fairly verbose version of this function. We then, on this next version, we then cut it down to just one line of code. The next version, we eliminate the return type and we just leave that as something that's implicit. And in the final instance, we even remove that return statement. And of course, methods, which we'll get onto later, but functions are called in the sort of standard method that one would expect. So you could foresee an instance where if you're writing lots of relatively simple code, using this sort of form of syntax is easier to write and easier to read. If you're writing something that was potentially like an API that other people needed to read, or you have a much more complicated expression, then perhaps using this sort of form of syntax is more appropriate. Or maybe you have a style guide that sort of stipulates something in the middle. It's really up to the developer. One more aspect of functions is that we support overloading, so slightly different from a language like Python. We also support var args, which is again more of a thing which was added to a more recent version of Java. We also support default parameters. So in this case, we have we have a function which calculates an expression contingent upon these default values which are fed into it. So we have a number of ways in which we could call this function. We can either pass no parameters, in which case all the defaults will use, or we can actually override. We can state some of those parameters if we so wish as well, by using another feature of the language, which is technically termed named parameters. You can use named parameters when invoking any method actually, but it's particularly useful for when invoking methods or functions that have default values. The language also supports exceptions. Now, so here's an example. So we define our exception class here, and then we have a function which performs some input validation. If the number's below 2, we spit out an exception. And then we have a fairly standard method of catching that exception within a try-catch block. Notice also that we're able to return values from that try-catch block, and we also support the standard sort of finally statements as well. Exceptions in Concurrens are what are known as unchecked exceptions, so you're not obliged to catch them. Now, the design rationale behind this is that exceptions are supposed to be exceptional. So if one is writing code, let's say you're reading something from a file, and one discovers that the file is missing. Rather than that is what we would consider to be an exceptional circumstance, as in away from the standard flow of operation, and so. But really, if that instance was considered to be part of the standard operation, then really it should be something that's incorporated within the core function of the actual function that we're defining. In which case, relying upon an exception in order to handle that particular erroneous case maybe is a bit of an anti-pattern, I think. So it's an open area of debate. Concurrence has gone down the path of unchecked exceptions. Seems to be the way modern languages are going these days. So anyway, now we have object-oriented programming. So within Concurrence, we have support for very, very compact definitions of classes. So here's a person class with two fields, actually three fields: name, surname, and likes. We have what's known as a default constructor, which is created automatically for us for creating that a person instance, which we invoke when we create the instance objects known as P2 here. Notice how the new keyword is optional, so you don't have to use it. You can use it if you wish, but it's up to you. We also explicitly define an additional constructor in this example, which will pass a default value to this more expanded version. We can call methods as normal. Now, with Concurrence, we also have the option of automatically generating what are known as setters and getters. So setters and getters in object-oriented programming languages are very, very important as far as supporting the concept of encapsulation is concerned. So Concurrence will automatically generate setters and getters for us, contingent upon how we specify the underlying variables, underlying fields of our class. So in this instance, by prefixing the name of the field with a tied character, Concurrence will automatically generate a getter and setter for us. When it comes to accessing fields, we can use this simple syntax, which is equivalent. So Concurrence will convert under the hood to make use of that getter on that instance object. The same when it comes to calling a setter, we can just use a standard assignment. So p.setName is the equivalent of this code here. We also get what's known as a copy, effectively a copy constructor. So these are created by default within Concurrence. You don't have to do extra work to support them. So if we want to make a simple deep copy of an object, we can simply do a one character operation in order to do that. We also for every single class, and you can, as a programmer, you can override this, but we define a equals and hashcode implementation, which means that you can perform an equality by value using the equals operator and have it behave in exactly the way that you would normally expect. In many object-oriented languages, this expression will perform equality via reference as opposed to equality by value. Whereas in Concurrence, this will map to this equals function, and Concurrence will also define an equals function for your class. So which I think does basically more of what people expect. The same could be said for the hashcode operator, which is very useful when working with data structures such as sets and hash maps. So in this instance, we have added two distinct, from a reference perspective, objects, but have equal value, and we're adding those into a set. And then when we look at the number of elements in the set, we find that there's just one, because there is only one from a value perspective. So again, this is the sort of functionality that people normally would want to have. We also have support for traits and generics, but we'll skip over these things for now. We also have support for enumerations, annotations, and there's also a with operator, but again, we'll skip over that. Concurrence is what's known as a null-safe language. So essentially, null is part of the type system of the language, and this is because having the concept of null in an object-oriented language is seen has been a bit of a design mistake. I think the person who invented it has referred to it as the $1 billion mistake. I think actually it probably costs a little bit more than that, but one of the major problems which most developers will face when using object-oriented programming is they will encounter null pointer exceptions. Well, if you don't have null, then you can't have a null pointer exception. But sometimes having null can be quite useful. So in those cases, one must be explicit about the fact that a variable can hold a null value. And so we signify that by postfixing a type with a question mark. And there's various ways, various degrees of support that are provided within the language for working with types that are nullable, including some interesting static code analysis, which allows one to work with null in a safe manner in cases where one has already asserted that something isn't already null. Or if, in this case, a branching operator, to get to this piece of code, a string cannot possibly be null because it's already catered for in this area here. We also have support for functional programming, and we'll skip over this for now. But I think the part which people are most interested in hearing about is concurrency. So it is unfortunate these days that to get to the most interesting part of the presentation, which is the concurrency, we have to have covered a lot of preliminary material. But this is just the nature of the beast. And if you want to build an amazing, like an engine for a car, for example, you still have to figure out how you're going to engineer the wheels, figure out the bodywork, figure out the seats, what type of lever are we going to use, is it going to be a digital dashboard, analog, etc. There's a lot of engineering work that you have to do around the core problem. But anyway, now finally we've got there. So isolates. So what is an isolate? So in Concurrence, we have the concept of multi-threaded programming. So an isolate is what's considered to be a lightweight thread. So in standard traditional concurrent programming, one would create a thread in order to perform a calculation on a concurrent basis. In a language like Java, it depends on how you set up your virtual machine and the system that you're running, but you're bounded maybe in, say, the tens of thousands on a standard machine. You're bounded, so you can't create more than 10,000 threads to operate on a concurrent basis. With Concurrence, however, we have a lightweight threading model that is not so much bound by the number of threads you can create, but rather it's bound by the amount of memory that you have. So you can get an order of magnitude or two, so 100,000 threads, 100,000 isolates or 1,000,000 isolates running on the same type of machine. So it scales much, much better. And the core concept here is using the bang operator in order to create an isolate. So here we have our code that we saw before to create our greatest common divisor, and this code is executed concurrently within an isolate, and isolates themselves are isolated from a memory perspective. Any dependent variables that they reference get copied into them, which of course is a little bit of a problem. If you're dealing with a very, very large data structure, you probably don't want to copy that into an isolate, but don't worry, we have support, which we're not going to cover in this presentation, but there is support for handling that particular use case through a keyword, through the shared keyword, and there's other methods as well. But in any case, dependencies are copied in, but isolates themselves aren't able to interact with the rest of your computer program on a shared memory basis. And so people will say, well, that's not very useful. I throw something into the box, it does something magical, and I don't ever get to see the result. So then we introduce the concept of a ref. So a ref type, and this is actually built into the type system of the language, is a standard type postfixed with the colon operator. And these are exceptions to the type system, or exceptions to the rule concerning isolation. They are controlled, shared components of mutable state. And in this instance here, so these two calculations will occur on a concurrent basis. When we come to perform the evaluation of the larger variable, we will wait for res1 and res2 to have completed calculation before we then are able to perform the calculation which takes place here in order to extract this larger result of the two. We also have an alternative way of achieving this is to use the await keyword. So if one spawns an isolate, returns a value in the form of a ref, one can use the await keyword in order to wait upon the result of that calculation having completed. Next here we have an example of two isolates which seem to modify a shared variable, but actually they don't. And this is just proof of the fact that isolates copy in their dependencies. And this is a very nice design decision, because it means that one can take a piece of concurrent code and run it on, say, a single core machine, or they can run it on a quad core or a 64 core machine, or they can run it on a distributed basis, and it'll behave in the same deterministic manner within the context of that code and within the context of the things which it interacts with. And so that allows the developer to be much more confident about the code which they're delivering and shipping. And this model actually allows us to support what's known as the reactive computing paradigm. So let's say if we're building some sort of trading system, we have two pipelines of reactive code known as two references, so two streams of asset prices coming into these refs that we have here. And then we have another piece of code here which says that every single time one of these two variables changes, perform a check on them, and if a certain condition is met, then go off and do my trading operation and then terminate further execution thereafter. Another example of this is below. So we have A and B, and we just want to calculate the sum of A and B, and we set the result of that calculation to C. So every time A or B, or both A and B change, we then are able to react to that change in those refs, and those changes may well be happening on a concurrent basis, and then spit out a result into C. And then we have another piece of code here which every time C changes, it would just print to our console that current value of C. And as with most aspects of concurrence, for code which one has to write a lot, there's a more compact syntax for it. So in one line, we are able to set up this reactive graph. Yeah, this reactive graph, if you will, in order to perform this operation. So every time A or B or both change on a concurrent basis, then recalculate and perform some calculation. In this case, very simple, just adding up. But you could imagine this if you were building, say, a derivatives pricing system in an investment bank. This could be your inputs to your derivative pricing, and then out would pop your asset price. We also support actors, which we'll skip over for now. We also have support for distributed computing built into the language, which again we'll skip over, and then we'll move on to GPU computing. So the rationale for this is that so a modern CPU, if you go to a shop now, you can buy just as a sort of a normal, like an everyday retail customer, you can buy a 64 core machine. I think it's AMD Threadripper something. I forget the name. 64 cores, quite a lot. It's quite a beefy machine. You can buy the same class, and for actually the same sort of money, you can go out and buy a GPU, of which you can have many within your standard machine, and many more in your server-based machine. And that GPU will have inside it up to 4,000 cores. So, okay, although it's the case that these cores within that GPU are the clock rate is much lower than your standard CPU, you have an order of magnitude or two or three more cores available to you. So then, and it's not surprising that nowadays many of the more recently produced supercomputers are basically just giant collections of GPUs with some CPUs to sort of control and move data here and there and interact with them. It makes sense from an architectural perspective. And the core of the GPU, the core concept is that you're operating the same program across multiple pieces of input data, which is different from a CPU-based architecture where you may be operating different bits of a program on different bits of data. With a GPU, it's slightly different, and that does introduce some caveats. And there are some things that one needs to bear in mind when one is programming on the GPU. Particularly around the way in which one interacts with memory. It's very much a manual process with the GPU, whereas with the CPU we don't really have to worry about it too much because we have what concepts such as level 1, level 2 cache, which essentially take care of making sure that the data that we expect to use or have most recently used is very near to where the calculation is going to be performed on the CPU. With the GPU, that process is much more explicit. We have to interact and control that a lot more, as we shall see. Now, Concurrent itself is the first language to have direct first-class citizen support for GPU computing. So one can write what we would call idiomatic Concurrent code. So this code looks very similar to just sort of normal code that you would write to do normal calculation on the GPU on the CPU. And you can take this, and so this is what's known as a GPU kernel. There are a few caveats, like we have to just declare what memory space our data exists within. It's optional, but it helps out the optimizer a little bit if we state if data is expected to be flowing into or out of a function, and we need to use. So in this instance, we have this concept of get global ID. So this calculation here is quite simple. We're just taking two vectors and then squaring the first one, adding the second one, and then adding a constant, and then returning that as the result. This get global ID will tell us will tell the instance of the kernel which is running on an individual core of the GPU which one it is and which parts of the data in this collection that it needs to be looking at. That's really about as complicated as it gets in order to leverage the GPU. You don't have to go off and learn very, very complicated C or C++. You don't have to you can be productive very, very quickly. You don't have to use weird compilation tool chains and switch into different products and this and that. Instead, it's just built into the language for free. Everyone gets it. All you need is to download Concurnas, have a GPU, which you probably have which you almost certainly have nowadays in a modern computer. You need to make sure you have the drivers that support GPU computing, and then away you go. You've got a supercomputer sitting next to you. And then there's some code here which is used in order to copy data onto that GPU, and also initiate that kernel computation. Notice also here that we're making use of our ref syntax. So this is a very nice feature of Concurnas. So all of these concepts of concurrency and parallelism, they're all together via use of the ref and via the use of isolates. So all of these, it's a cohesive model. Like when we're writing code to operate on the GPU, we're not having to switch into a different programming paradigm. Rather, we're just using what's considered normal within Concurnas. And one of the key motivations for this is that copying data to and from a GPU is usually the slowest part of the actual overall pipeline of calculation on the GPU. And so what we want to be doing is keeping the GPU as busy as possible. So we can concurrently copy onto the GPU, we can concurrently copy off the GPU, we can concurrently run execution on the GPU. And by using the ref style syntax here, we're able to do that. So Concurnas has a lot of support for working with data, which I feel that we've touched upon quite nicely within this talk so far. So we'll skip over these parts for now. We're also able to run other languages within Concurnas. So I think my favorite example is this. So here's an example of some APL. So APL is an interesting sort of experimental, but real production language. And it is characterized by the use of these strange characters, which all have proper names for them. And the way in which one used to program and write APL is you'd have a special sort of typist sort of ball that you would use, and which would then which had all of these special symbols within it. So I don't know, good luck if you wanted to add a new symbol to do some special operation. You'd have to figure out how to get that onto the ball somehow. But yeah, very interesting. It's inspired a lot of other languages. I think KDB, or sort of the Q language, is one of the ones which is expired. And this piece of code, believe it or not, will give you 6 unique random numbers from 1 to 40. And yes, if you so pleased, you could embed APL code into your Concurnas code. I think more likely, and we've not delivered this yet, but this will be coming soon, we'll have some sort of SQL or declarative programming type syntax. So you'll be able to embed SQL into your Concurnas code, and that code itself will be able to interact with other code that you have defined within your Concurnas program. So it can call other functions, it can produce functions, and it can also interact with the compiler at compilation time in order to make the development process so easy for people to work with. So that's most of the code. We've skipped over a lot of things, and there's a lot of things that are not covered in the slides, but which are covered on the website, and more details and links will be provided very shortly. Some very interesting things that we don't have enough time, or probably talks in their own right. Off-heap memory management. So Concurnas offers a method by which you can work with more data than can actually fit in the RAM of your machine, and it will help you to interact with that, and you can spill off data onto disk. You can work with very, very large data sets. We also have support for domain-specific languages through features such as extension functions, expression lists, and operator overloading. We also have support for object providers, which are a mechanism for performing dependency injection when you're creating object graphs. We also have the concept of type defs, which are sometimes when doing object-oriented programming, you end up with situations where you have a list of a set of a hash map of a list of a list of a hash, and so on and so forth. You end up with these very, very long definitions. So Concurnas essentially provides macros which help to collapse and reduce those very, very long definitions in the form of type defs. We also have what's known as lazy evaluation, which is another concept from functional programming. We also have the concept of traits, trait stacking, inheritance, so the standard stuff that you'd expect to see in object-oriented programming languages. We also have things like smart casting. And one of the questions people ask is, well, what about performance? You've got all this great functionality. Doesn't surely this costs a lot, right? I mean, it is true that there is some overhead associated with the concurrency model that's presented within Concurnas. That overhead is in the order of about 5%. That's quite reasonable, I think, given the advantages that are provided by the model that is exposed within Concurnas from a developer perspective. Developer productivity perspective, and by virtue of the fact that the code that developers are creating is easier to reason about. And people are often surprised about the fact that we've chosen the Java virtual machine to run Concurnas. And I think this is because earlier versions of Java were essentially interpreted. So they ran very, very slowly. And I think that Java never really that sort of tarnished its image slightly. So particularly within the high performance computing space, where people, where languages like C or C++ or even Fortran are still very much used. And people say, oh no, Java's slow. Well, actually modern day versions of Java are not really that slow. They're kind of on a par with C and C++. You've also got things like garbage collection, which you get for free by running on the JVM. And the JVM itself is always improving. Every single new release of the JVM has added extra performance. So Concurnas essentially gets this for free, and actually any language which runs on the JVM, whether it be Java, Scala, Kotlin, etc., they also get that for free. And it's something which I've spoken to some people who maintain the JVM at Oracle, and they're very, very committed on stability and also improving that virtual machine. So the future's looking bright. And as far as the future for Concurnas is concerned, there are a few key initiatives that we're looking at. So better development tools. So I'll hold up my hand and say that one mistake that I made when building the language was not putting enough effort into upfront building an IDE. So this is the number one request that I get on our Discord servers. People say, oh, I love the language, I really want to use it, but I really, really wish I had an IDE. I wish the developer tools were better. I wish I had a documentation generator. I wish I had a code formatter. There's a contributor on in the open source community, and you can go and speak to the person on the Discord server if you wish, who's building a Gradle plugin. So that will help. That helps with building software, with building Concurnas and fitting Concurnas code into projects which use other JVM-based languages, or even, or I'm pretty sure Gradle supports non-JVM languages as well, like C, C++. So anyway, it's all there. It's all coming together. We also want to have better off-heap memory management support. I think a very interesting project, and something I've wanted to do for a long, long time, but would be able to build, say, a database system like a MySQL or a MongoDB within Concurnas. I think databases as products, I feel that that's a bit of a strange place for the world to be, and I feel that given the amount of, like, most enterprise software, at least let's say about 90% use databases in some way, I think it's perhaps time for databases to be shifted into the programming language space, just to give developers a little bit more control. And adding better support for off-heap memory management would enable that sort of development. Want to have better GPU computing. So what exists at the moment is actually very useful for people. But I think that there's lots of things we can do in order to improve that experience. The compiler at the moment is a little bit slow. I think we can probably increase the compilation speed of Concurnas code by at least an order of magnitude, or maybe even 2. The most important thing, though, is that the runtime is actually really quick. So once you've compiled your code and got over the slight delay you'd incur there, when it comes to actually running your code, say in a production environment or just if you're doing a debugging, etc., it's really quick. So we've solved the most important part of the problem, and now we just need to go back and improve the speed of the compiler. And another very interesting thing which we're looking to add in support of some customers in the finance community, and also in order to attract people who work in machine learning to using Concurnas, is automatic differentiation. Actually have support for that at a language level, and then Concurnas will be the second programming language in the world, in addition to what's the one by Apple? I don't remember. There's a programming language produced by Apple, and they have support for automatic differentiation. So we will be the next language to have support for that. So yeah, Concurnas. So this is my company. We offer commercial support for Concurnas. We offer consulting. So that's language development. Also within financial services, enterprise computing. Within the the FANG space as well, and we also offer sponsor development. So if there's a feature you'd love to see in Concurnas, get in touch, and we can. It will probably be cheaper for you to have us implement it than it is for your own developers to implement that feature and then contribute it as open source. But yeah, it's open. You can have that conversation if there's something that you'd like to see, and we're very open to making non-breaking, non-too revolutionary changes. More information can be found about Concurnas on our website, so concurnas.com. There's documentation, there's articles there, videos, there's details about how to download from there as well, or you can use what's known as SDKman, which is a package manager, which is a distribution platform for JVM based languages and JVM distributions. You can come and join us on our Discord server for help, support, chat, etc. And if you're interested in contributing, then all of the code is open source. It's all hosted on GitHub, and we're very accepting of pull requests. And we will work with you in order to make Concurnas the best language that it can possibly be now, today, tomorrow, and for at least the next 30 years. And that wraps up the presentation. And ready for any questions.
There have been a few questions on the chat. The first one is from Bogdan Stroh. What about Scala futures?
So I'll answer the question just more generally. And I don't, this isn't really my personal opinion, so to speak, but I found that the consensus of Scala is that it's a very complicated language. I don't personally think that's fair. I quite like Scala actually. I've programmed in it in the past, and a lot of the ideas within Concurnas are actually, so for instance, traits are actually lifted from Scala, and I hope that the contributions which are within Concurnas will also be lifted, and maybe some of them will find their way into Scala, maybe some will find their way into Kotlin, maybe some will come into Java. But in essence, I feel that the consensus of opinion is that Scala is a very complicated language, and too complicated for people to understand. So yeah, I've actually used Scala futures before, but I think that the fact that they're embedded within Scala, I just think it frightens away too many people. It's just one of those things.
There is a question from Wei Wu. Does it support AMD GPUs?
Yes, we do. Yes, okay. So that's a very good question. So when we were first designing Concurnas, we had the option of integrating onto the GPU using one of two methods. We could either go down the OpenCL path, or we could go down the NVIDIA CUDA path. If we went down the CUDA path, then we would only be able to support NVIDIA GPUs. So we decided to go down the path of OpenCL. So both AMD and NVIDIA GPUs are supported. So some people, there's this perception that that CUDA is much quicker than OpenCL. I'm not really sure about that. I've not seen enough evidence one way or another. Depends on who you ask and who's doing the benchmark. Sometimes OpenCL is quicker, sometimes CUDA is quicker. If there's interest in a NVIDIA backend, we're open to producing that. That could either be through sponsor development, or if there's enough interest, and we can do a CUDA backend if people so wish. But the core GPU support is within Concurnas is sort of essentially agnostic to both the middleware that we use to communicate with the GPU and the actual underlying GPU itself.
Another question from Don McGimpsey. Are Python libraries supported?
That's actually a very good question. Yes, because in the Apple language Swift, yes, they have support, so you can actually call into Python from Swift. This is not something which is supported in Concurnas at the moment, but that is a very interesting idea, and something that's on a notepad somewhere. So yeah, that may well be something that we look towards supporting in the future. Of course, the obvious use case there would be being able to leverage something like like TensorFlow, which has a very nice Python-based interface presented to it that people can use. But being able to integrate more directly with Python is a very interesting idea. You can sort of achieve it at the moment via the use of language extensions, as we covered previously. But I think we could probably do a little bit more work in that way to go along the lines that the Swift language has taken.
There is a comment from Andres Berenguer Alonso. Is Swift the Apple's code that you wanted to refer to?
Yes, it is. Thank you.
And there is a question from DMM. Where did isolates come from? Are those your invention?
Okay, so it's an interesting story about that one. So I was when I was working in JP Morgan, I wasn't working on Concurnas at that time. I was just focusing on my job, but all of these ideas and problems were sort of in my mind, and I was sort of thinking about them. And there was a time when I was in a conference in Dubai, and I was talking about derivatives, about FX options and our trading platform. And I was in the shower, and I was actually thinking about these programming problems. And I thought, well, how could we solve this? Like, what we really need is a lightweight thread, and so I thought, well, let's do isolates. And then I did a bit more research, and then I discovered, okay, actually, it's not my idea. It's a concept that's actually existed since, I think, maybe the 60s, but it's been popularized in languages such as Google Go most recently, but also Erlang. So they have a very similar concept of this lightweight thread, which is isolated from everything else operating within the program space, that has its own memory space, controlled way of communicating. I think the Google Go concept of isolates is slightly less strict than the one which is presented within Concurnas. And then the Erlang one is very similar to Concurnas as well, but it's a functional language which sort of frightens people off. So I would like to believe it's my invention, but upon further investigation, actually no, the ideas have been around for a very, very long time.
And there is a question from Fajindar Ladat. Is there any unit testing framework available with the language?
By virtue of the fact we run on the JVM, you have access to the wealth of Java libraries that are around right now, including JUnit. So I when we were building Concurnas, so part of Concurnas, the language itself, the majority is written in Java. The remaining is written in Concurnas itself, which makes the build very fun. So what happens is we'll build the language to a certain point, and then it'll then bootstrap and build the rest of itself from the Concurnas code, which is actually written in the Concurnas language, and then it will then distribute and produce a package and a runtime and so on and so forth. But we actually leverage JUnit throughout that process for all of our unit tests, of which there's about 40,000 unit tests that are that support the actual core language itself. It's about 600,000 lines of code, both in Concurnas and Java. But yes, I would recommend using JUnit.
So if there are any further questions, you can put them on the chat. So you guys have probably... Oh, there is a question. Any comparison to Julia? The question from Weiwu.
So I've not looked into Julia in a tremendous amount of detail. I think it's a very nice language. I think it's very promising. I've read the feedback that I've read about it is that some people don't like... They think... there are some aspects of it that are slightly quirky. Like I think the way that you've got to explicitly terminate blocks of code, I think you've got to use like an end statement or something like that. I think people don't like that aspect of its design very much. But yes, we actually get that comparison with Julia quite often. I think one very interesting thing about Julia, and I've actually spoken to the creators of the language I think about this, is that it's been designed to solve a specific problem. So it's particularly in the numerical computing space, it was dominated by languages such as MATLAB, and there's a clone of MATLAB, I think Octave, something like that. And you've also got languages like R, and all of these languages are that no language is perfect, but Julia aims to solve a lot of those problems which are presented in the language and provide, again, like Concurnas, a dynamically typed like syntax, whilst also providing the C-like performance. So yeah, this is again a goal which Concurnas has aimed for. So yeah, I see I do see the comparison there. The one thing I would say is that Concurnas is explicitly designed for solving the concurrent programming problem, whereas I think Julia is a bit more aligned towards numerical computing. But yeah, no, really interesting language. Fascinating team behind it. Quite a bit of history. I think it's been around for like 10 years or so. It's going to be interesting to see where Concurnas is at in 10 years' time as well.
There is a question from Thomas Schorsch. Can Concurnas be called from other JVM languages?
Yes, it can. There's actually, in the next release of the language, which will be probably the next month, there's some patches going in to make that process much, much easier. At the moment, it's a little bit tricky, but yeah, that's something that is going to be is much easier to work with very soon.
And there is a question from DMM. He's saying it's quite involved, so feel free to skip it. Just curious what makes a thread lightweight or heavyweight. Thought it was just a memory space in the chain of execution.
There's a really, really good article about this. So if you search for Project Loom, and which is a Java project, which is an Oracle initiative to add the concept of continuations to the JVM. There's a really good, very long article about what continuations are and the concept of a lightweight thread. I think that probably explains it much better than I can in a few minutes. But yeah, so just search for that Project Loom, and there's an article about continuations. So in that search space, very long one. I think it's hosted on. I think it's either on the OpenJDK website, or it might be like an idea on GitHub. One of these essays that people write. But that explains the concept of a continuation.
So there is a question from Andres Bringuier Alonso. Can you declare a non-nullable variable without initializing? Will it get a default value?
Yes, you can. So you could say my string, and then that's it. You leave it at that. That is not assigned the null value. It's just assigned nothing within the context of the program. So if you then don't assign it something, Concurrens will flag that up and say, well, hey, you've created a variable, or you've defined a variable, but you've never assigned anything to it. It's not going to cheat and then assign null to it anyway. No, you don't need to worry about that.
As I see, there are no further questions. So, Jason, we would like to thank you for an excellent talk. Thank you very much for giving a Thalesian talk on concurrence. I think everybody has enjoyed it. There is another comment from Saeed saying, great talk, thanks for speaking. DMM is saying, very impressive. Weiwu is saying, thanks for a great talk. So there are quite a few thank yous on the chat for Bogdan Stroy. I'll very quickly just announce that we have in this seminar series more comments, more thank yous from Thomas Schorsch, Sumit Mahivia Sethi, Holger, Elias Burshad, Andres Brengiao. So everyone is commenting that they have found this talk very interesting. I'll very quickly mention that we have a few more forthcoming talks. On May 28th, we have a free webinar by Nicholas Houch, Limits to Arbitrage in Blockchain-Based Markets. On June 3rd, we have Marcus Lopez de Prado, ML Solutions to the Bias Variance Dilemma. On June 11th, we have a free webinar by Marcus Hoffer, Quantifying Systemic Risk Using Bayesian Statistics. And on June 17th, we have a free webinar, Machine Learning and the Fight Against COVID-19, an introduction to molecular machine learning and drug discovery using open source tools. So this is what we have planned, and we hope that you will sign up on the website meetup.com/Thalesians, and we hope that you will also join us to watch the videos on www.thalesians.com/videos. Thank you all for coming. Thank you very much.
Bye-bye.
Bye.